Hello everyone, my name is Ruei-Che, and I will be presenting Daedalus in the Dark, designing for non-visual accessible construction of laser card architecture. I would like to thank Tom Ye and Bingyu Chen for guiding this project, and my colleagues Zhian, Fangying, and Serafina for their hard work. Let's look at how Daedalus works. Daedalus is a Fusion 360 plugin. In Daedalus, designers can add ground support for the model in order to stabilize the assembly process for blind or low vision people. Daedalus automatically generates an 2D layout encompassing different tactile aids and spatial arrangements, such as symmetry or layering order. Designers can fine-tune the layout in Daedalus, such as fitting the components within the board. Daedalus sets constraints for the manual edits in order to maintain the accessibility heuristics that we identified from a formative study. Finally, Daedalus generates a file ready to print by a laser cutter. Let's look at our first user study and findings that inform the design of Daedalus and the tactile aids. To understand the accessibility barriers, we first conducted a formative study with 7 blind participants. We started with the learning session, where our participants were introduced to 3 commonly used joints, including finger joint, slot joint, and multi-tendon joint, by practicing some example models of them. After familiarizing with the joints, participants were asked to assemble 5 laser cut models in a testing session. Each of the 5 assembly tasks had specified time thresholds, and we recorded the completion accuracy of each task as performance measurement. Completion accuracy was measured as the number of correctly assembled joints out of the total joints in a model. Finally, we held a co-design session where participants were encouraged to speak about the barriers they encountered in testing session and potential solutions to address them. We also provided some crafting materials for our participants to express their thoughts on designing tactile aids. Our study identified a number of difficulties. For example, participants spent much time deciding which piece to start with, and most of them expressed wanting to start from a core component that can quickly form a stable structure. Participants also had difficulty in identifying the correct joint parts to pair. During assembly, it's hard to stabilize the mid-assembled model when assembling other pieces without vision, and the model was prone to collapsing. Some models had symmetrical pieces, which took much time for our participants to identify. Unlike in vision, they need to touch every detail to confirm the symmetry. Some models require fixed assembly order, which was hard for blind participants to observe. The wrong assembling would incur additional effort in removing the assembled pieces and reassembling. To mitigate these barriers, we co-designed the tactile aids with our participants. We designed a large hollowed circle on the bottom right corner of the plate, which links to the first component with a tactile line. Users can follow the tactile lines and arrows to find component pairs. The area surrounding a joint is hollowed out in half circle to allow components to be easily lifted from the plate. After assembling the first few components, participants can place them into the ground support to make the remaining assembly more stable. To address the problem of fixed order, components are arranged from bottom up and layered based on their proximity to the entry component. Users can also place the model back into the plate to quickly access the tactile hints. We also arrange symmetrical components to be mirrored. This way, participants don't need to spend additional time finding symmetrical pieces. Here, we briefly describe the rationale of layout generation. Given input model and joint inputs, each component is taken as a vertex, including the ground support, and each joint is taken as edge to build an undirected graph. Based on this graph, we conduct breadth-first search to build the tree. Finally, we add the ground support to the tree, which will be layered above the 2 components it connects with. Given this assembly graph, we used a star search to find the optimal path for engraving tactile lines. We can finally generate a layout in Fusion 360 for further edits by the designer. Detection of joint types, their length, and location is required for more accurate integration of tactile edges. Our method is to classify joint pattern of the endpoints of the contours. More details can be found in our paper. To evaluate the tactile edges, we ran another study with 8 blind participants. We had a learning session to introduce the 3 most commonly used joints, same as in the first study, and also introduced all tactile edges we designed. In the testing session, participants were also asked to assemble the same 5 models from the first study. But this time they used the plate and tactile edges generated by Daedalus. In this evaluation, we found that participants were able to follow the tactile lines and arrows to find the joint pairs. With the ground support, the mid-assembled model remained stable during assembly. We also found that participants were able to place the model back to access pairing hints more efficiently. These are the results of our 2 studies. The bars represent the completion accuracy of each task. By using our designed tactile edges, participants in second study had better performance overall on the assembly tasks. Feel free to read our paper for more details. Thank you for listening.